Okay, so I decided to talk about adjacency matrices, which I said at the beginning of chapter 2, I said I'm going to skip this for the time being. And I guess I did, but I said I might come back to it, and so now I'm coming back to it. So that was fast. I would recommend reading the part of chapter 2 about adjacency matrices before watching this video. So I'll sort of get right into it. So assuming you've read the general definition of adjacency matrix, I'm just going to show you an example here. Here's a graph. I've labeled the vertices V1 through V5, and here is its adjacency matrix. The adjacency matrix is just a matrix. It's 5 by 5 because this has 5 vertices. Each row corresponds to a particular vertex, or sorry, I pointed to these and called them rows. These are columns. The vertical ones are columns. So this is like the V1 column, V2, V3, V4, V5, but also each row corresponds to a vertex. This is the V1 row, V2, V3, V4, V5. And the zeros and ones just tell you which vertices are adjacent. So, for example, V1 and V2 are adjacent, right? I see that they're here. So there's a 1 telling you V1 and V2 are adjacent in the V1 row and the V2 column. By the way, there's also a 1 right here, and that's telling you the same thing, because this is the row for V2 and the column for V1. Meanwhile, let's say V1 and V3 are not adjacent, so I see a 0 here. By the way, of course, I also see a 0 here for the same reason, because V3 and V1 are not adjacent. And right, just pointing at the picture to point at everything, V1 and V3 are sure enough not adjacent in the picture. So that's why there's a 0 here and a 0 here. In a graph, a vertex can't be adjacent to itself, so you have a 0 telling you that V1 isn't adjacent to itself. You also have a 0 here telling you that V2 is not adjacent to itself. In fact, we would have zeros all the way down the diagonal. In an adjacency matrix, that's always true. You always have zeros down the diagonal, and it's also what we call a symmetric matrix, because there's some redundancy in this matrix. If I put my pen here down the diagonal, the information that I see above my pen is basically an exact copy of the information I see below my pen. For example, this 1 and this 1 are telling me the exact same information. It's just telling me that V1 is adjacent to V2. This is a symmetric matrix, meaning that it's like a mirror image of itself above the diagonal and below the diagonal. Okay, so we have this method of storing the information of a graph in its adjacency matrix. If you give me a graph, I can draw its adjacency matrix. I just have to make a big enough square matrix and fill it out with zeros and ones based on the picture of the graph that you gave me. You tell me which vertices are adjacent to each other, and then I fill in the zeros and ones accordingly. Also, if you gave me the adjacency matrix, I could draw you a graph that has that adjacency matrix, as long as the matrix that you give me follows the reasonable rules. In order to be an adjacency matrix, it has to have zeros down the diagonal, and it has to be symmetric above and below the diagonal, like we discussed. But as long as you give me a matrix full of ones and zeros that satisfies that, I can then draw you a graph, because the matrix that you give me is exactly telling me which edges to draw, and so that's all the information I need to draw the graph. So what we have here is a way of storing the information from a graph. We can store it in the form of a matrix. And when people start talking about adjacency matrices and thinking about them, it's not clear that that's really useful. Why do I need two different ways of representing a graph? I already have this way. I can just draw it. Looking at this matrix, it's kind of hard for me to look at this and tell what are important facts about the graph that we're talking about. It's all just sort of hidden in the zeros and ones. So there's a real question of why is it useful to store information in an adjacency matrix? And maybe a better question is what are the things that we typically do with matrices, and what could they possibly tell us about the graph? Like when you learn about matrices, you can add matrices together, you can find a matrix inverse, you can multiply a matrix by another matrix, you can find, and by the way, linear algebra is not a prerequisite for this course, so I don't assume that you're all experts in matrices, but many of you have probably heard of eigenvalues and eigenvectors, and those are things you can find from matrices. And so I guess the general question that I'm asking is, do these typical matrix operations actually tell us anything about the graph? And surprisingly, maybe the answer is yes. I'm going to talk about one of those ways today. In particular, it's matrix multiplication is what I'm going to talk about. What does matrix multiplication and adjacency matrices, what can that tell you about a graph? Well, so we have Theorem 2.2 in the book. Basically, this theorem says that if we have a graph with a vertex set v1 through vn, and it has a particular adjacency matrix A, and if what I do is I'm going to look at a power of the adjacency matrix, a to the kth power, meaning a times a times a, k times. We're going to look at the ij entry. By the way, this just means the entry in the matrix in the ith row and the jth column. That entry of this matrix tells you the number of walks from the vertex vi to the vertex vj of length k. So let's take a moment to think about what that means. For example, here's a squared. Let me just sort of pick on a particular entry in a squared. Maybe say this entry. This is so these are corresponding to these vertices, and let me go down as well. So what I just circled, this would be the 2, 4 entry. It's in the second row, 1, 2. It's in the fourth column, 1, 2, 3, 4. So this is the 2, 4 entry. And this should tell us the number of, according to this theorem, the 2, 4 entry of a squared should tell us the number of v2, v4 walks of length 2. And now let's look at the graph. How many v2, v4 walks are there of length 2? Well, I could go this way. This is a walk of length 2. I could start at v2, then go to v3, then go to v4. I could also do this walk of length 2. Start at V2, then go to V5, and then go to V4. And those are the only two walks of length 2 that start here and end here. That's why this is a 2. Let's maybe look at something else, like, how about this 3? So this is the 2-2 entry. This is the second row in the second column. So this should tell us the number of walks that start at V2 and end at V2 and have length 2. So let's look at the graph. I'm thinking of walks of length 2 that start and end at V2. And if you think about it, the only way to do this is to... So a walk, it starts at V2, and then it goes to a neighbor, and then it goes to a neighbor of that, and then a neighbor of that. But this is just a walk of length 2, so I have to start at V2 and then go to a neighbor, and then go to a neighbor of that, and I had better be at V2 because it's supposed to end at V2. So the only way to do it is to basically go to V2, go to a neighbor, and then go straight back. That's the only way to take 2 steps and end back at V2, is if I go to a neighbor and then come back. And how many ways can I do that? That's supposed to be this number, so there's supposed to be 3 ways to do that, and there are. I can go here and come back, I can go here and come back, or I can go here and come back. There are 3 walks of length 2 that start at V2 and end at V2. Why don't we look at A cubed? And by the way, I used a computer to do this matrix multiplication. I didn't do it by hand. I mean, it's not that hard to do by hand. It's just maybe a little time consuming. But let's take a look at A cubed, and maybe, let's see here. Why don't I look at this? I just want to circle an entry here and explain it. Maybe let's look at this 5. So this would be, so this is in the 3rd row, 2nd column. So this is the 3-2 entry of A cubed. This should tell me the number of walks of length 3, because that's the power, from this vertex to this vertex. So the vertex V3 to the vertex V2. Okay. There's supposed to be 5 of them. Actually, let me even list them out. These are supposed to be walks of length 3 that start at V3 and end at V2. So if you'll just bear with me. There's supposed to be 5 of them. Okay. Well, it's a walk of length 3. So one way is I could go here, I can go back, and then back. That's 3 steps. 1, 2, 3. In other words, I would go V3, V2, V3, V2. That's one of them. I could also go from V3 to V2, and that's one step, and then I can make two steps by going here and back, or here and back. So in other words, I can go V3 to V2, and then V5 and then V2. Or I could go V3 and then V2, and then V1 and then V2. So that's 3 walks. Let's see. I can also go around this way, right? This is 3 steps. 1, 2, 3. So V3, V4, V5, V2. V3, V4, V5, V2. And there's supposed to be one more way, because this is a 5, and I think I know it. It's going to be one. I mean, some of these walks. Of course, a walk is, if you recall, a walk is allowed to repeat edges and repeat vertices. All you have to do is to go to a neighbor and then go to a neighbor of that and then go to a neighbor of that. So you can kind of kill time by just going back and forth from a vertex to another vertex, and we found many walks by doing that way. I think I see one more way to do it. I can go from V3 to V4 and then back and then to V2. That's 3 steps. 1, 2, 3. So V3, V4, V3, V2. So I found 5 of them. So that's how it's supposed to work, and that's what this theorem is saying. But of course, this isn't a proof of the theorem. So let's talk about a proof of the theorem. The theorem, the proof will be by induction on K. K is the number where, so we're talking about a to the kth power, and we're saying that the ij entry of that matrix counts the number of vi, vj walks of length k. So we're going to do induction on that number, k. And the base case is k equals 1. The theorem is for k greater than or equal to 1, so that's the smallest value of k we'll consider. That's actually easy because a to the 1 is just the original adjacency matrix. The adjacency matrix has a 0 if you don't have an edge from vi to vj, and it has a 1 if you do have an edge from vi to vj. In other words, this is precisely counting the number of walks of length 1. Walks of length 1 are very simple. The only way to have a walk of length 1 is to start at a vertex and then go to one of its neighbors. So if 2 vertices are neighbors, then there's going to be exactly one walk of length 1 from one vertex to the other. And that 1 in the adjacency matrix is telling you that. That's telling you there's one walk of length 1 because they are neighbors. If they're not neighbors, then there's no walks of length 1 from vi to vj. The only way to have a walk of length 1 is to have there be an edge there from vi to vj. And if there's not, then the adjacency matrix has a 0 there, which is the number of walks. So for walks of length 1, A is telling you the right answer. It's telling you the number of walks from vi to vj. And that's the base case here. So let's talk about the induction step. So we're going to assume that the theorem holds for a particular value of k. I'm going to say k prime. And then I'm going to use that to prove that it holds for the next value of k, k prime plus 1. So we're going to use some notation here. let a sub ij, and then this looks like a power, but it's not. This is indicating that this k is indicating that we're doing the power of the matrix. So we're calculating this matrix power. So I multiply the matrix times itself k times, and then I look at the ij entry of that, and that's what this is. Then the way that I'm going to count these walks is as follows. So once again, this is by induction, so I'm assuming that the statement is true for k prime. In other words, if I look at a sub ij with a k prime there, then that really is telling me the number of walks of length k prime that start at vi and end at vj. And then the question is, how do I count walks of length k prime plus 1? Because this is induction and I have to go from k prime to k prime plus 1. So I'm going to count the number of walks of length k prime plus 1 as follows. To do a walk of that starts at vi and ends at vj of length k prime plus 1, first I have to do a walk of length k prime starting at vi, and I have to do a walk of length k prime, and I'm going to like the second to last step, because in one additional step I have to get to vj. In other words, my walk of length k prime has to end at a neighbor of vj. That way I'll be able to get to vj in one more step. So I count it this way. This is just saying I'm going to add up, and what I'm going to do is for every neighbor of vj, because once again, what I have to do is I have to start at vi and then take a walk of length k prime, and that has to end at a neighbor of vj. So for every neighbor of vj, in other words, every vertex v sub l that's in the neighborhood of vj, what I'm going to do is I'm going to add up how many walks of length k prime start at vi and end at whatever that neighbor is. Actually, maybe a small picture is in order here. This wavy line just represents a walk of length k prime. This straighter line is just a single edge. So I have to start at v1, take a walk of length k prime to end up here, and then go straight to vj. There may, of course, be many walks of length k prime. So, but however many there are, each one gives me a way to get to vj. So I'll count all of them. In other words, for every neighbor of vj, what I'm going to add up is how many walks of length k prime are there to get from vi to vl. And of course, in this picture, this is just one particular neighbor of vj. I'm doing this for every neighbor of vj. So there may be another vertex down here and a bunch of walks of length k prime to get here, and I would add all of those too. So that's what I'm adding up. I rewrote that last sum here. This is just the same exact thing from the last line. Unfortunately, I have to start a new page, but I just rewrote the very last thing. And I can rewrite this sum as follows. I can write it this way. How is this different? So Over here, this was a sum just over the L's, the values of L such that V sub L is a neighbor of Vj. So there's just certain values of L that are taking part in this sum. In this sum, I'm summing over every possible value of L, just from all the way from 1 to n. This number is the same as it was, and what I'm multiplying it by is this number. This so this number is just a sub Lj. This is meant to be an entry in the original adjacency matrix. So this number is either a 1 or a 0, and in particular, this is basically 1 if VL, Vj is an edge, and it's 0 otherwise. When I do a scribble here, this just means otherwise if I'm doing like a piecewise function, right? Because that's what the adjacency matrix does. It's either a 0 or a 1, and it's a 1 if there's an edge there, and if it's a 0 if not. In other words, this is doing the exact right thing. Since I'm summing over all the values of L, but I really only want to add these numbers for the values of L that are neighbors, such that VL is a neighbor of Vj. This does exactly that. In other words, the values of L for which this is 0 are the values of L that I don't want to include in the sum. And the values of L such that this is 1, those are the values that I do want to include in the sum. So it does the right thing. Right? Because this sum is only over the values of L that are neighbors of Vj. And that's precisely where you would have a 1 here instead of a 0. Because if VL is a neighbor of Vj, then you have a 1 here, and if not, you have a 0 here. So these are the same thing. And this looks just like matrix multiplication. How do you do matrix multiplication? If I were multiplying the matrix A to the K prime by A in order to get the matrix A to the K prime plus 1, what would I do? The way you multiply matrices is if I want to find the ij entry of this matrix, what I do is I go across the ith row and down the jth column, and I do this times this, plus this times this, plus this times this, all the way until I'm at the end, until I'm doing this times this. In other words, it's exactly this sum. So this sum, where I'm going across this row of the A to the K prime matrix and down this column of the A matrix, that tells you the aij entry of the matrix A to the K prime plus 1. In other words, this is that number of walks that we were trying to count. It is the number of walks from Vi to Vj of length K prime plus 1. So that can be a tough proof to understand. It's not that bad. You have to really remember how matrix multiplication works, and you have to follow this funny step. But it's not that bad. It's probably on the harder side for proofs for this class, though. So I'd like to illustrate it. Going back to our particular graph and our particular matrix. We had this graph, and this was the adjacency matrix, and I showed you a squared and a cubed. Let's talk about just the act of performing matrix multiplication in order to get a cubed. So I'm doing a squared times a. As long as you trust me that this is a squared, I just copied the answer from here. We will perform matrix multiplication, or at least we'll do a little bit of it. I'm not going to do the whole thing because it's a 5 by 5 matrix. But we'll illustrate the theorem. And yeah, actually, I was going to do the 2, 5 entry, but why don't we, since before we kind of looked at this 3, 2 entry, so maybe I'll focus on this one, the 3, 2 entry. So that's like the entry that would be here. And I know, well, I know because I used a computer to calculate the answer, I know that's supposed to be a 5. But let's really do it. To verify this number here, again, this is the 3, 2 entry. That's the third row, second column. So what I do is I look at the third row of this and the second column of this. And I do this times this, plus this times this, plus this times this. So in other words, I'll really write it out here. 1 times 1 plus 0 times 0 plus 2 times 1 plus 0 times 0 plus 2 times 1. And that better be 5 or I'm going to be mad. It is. So that's how you would calculate this. But let me, since this is supposed to be an illustration of the theorem, let's talk about, again, why is this doing the right thing? Basically, this one, for example, tells me that there is one walk of length 2 that starts at V3 and ends at V1. And that's true by looking at the graph. There is one walk of length 2 that starts at V3 and ends at V1. It's the walk that goes here, here, and here. There's no other way to get to V1 in 2 steps. You just have to go here and then here. So that's this one. So this one is here. That got multiplied by this one. This one is just telling me that V1 is a neighbor of V2, which is, when we put that together, when we put together the fact that there's one walk of length 2 from V3 to V1, let me even write this down. There is one walk of length 2 from V3 to V1, and there's one edge from V1 to V2, that gives me one walk of length 3 from V3 to V2. And I get that walk of length 3 by, first I take this walk of length 2 from V3 to V1, And then I get from V1 to V2 using this edge. Let me pick something else out of here and just explain it. Maybe I'll do a quick one. This is 0 times 0. This 0 came from here. This 0 came from here. And I'm going to say some silly things because it's 0, but this 0 just tells me that there, so this would be, this 0 tells me that there are 0 V3, V2 walks of length 2. And looking at the picture, that makes sense. I can see a walk of length 1 from V3 to V2, but I don't see any walks of length exactly 2 from V3 to V2. And this 0 is telling me that basically I can't, there isn't an edge from V2 to V2. So this isn't giving us anything. That's why it's 0 times 0. Maybe let me focus on something slightly more interesting, like maybe this 2 times 1. So this 2 came from this 2. And this 1 came from this 1. This 2 is telling me, let me put all of the labels here. This 2 is telling me that there are 2 walks of length 2 from V3 to V5. And this 1 is telling me that there's an edge from V5 to V2. So this is telling me that there's 2 V3, V5 walks of length 2, and I don't really need to keep verifying this, but I like looking at the picture to just keep saying that, yes, this makes sense. So I can go this way, or I can go that way. I see 2 walks of length 2 from V3 to V5. And either one of those can be finished off by taking the edge from V5 to V2. Because remember, this thing that we're calculating, this 5, it's this entry. It's supposed to be the number of walks from V3 to V2 of length 3. And I can find 2 of them by taking either of the walks of length 2 from V3 to V5. I can either go this way or go this way. And then whichever one of those I do, then I can take one more step to go directly to V2. And so that gives me 2 ways. And I didn't explain this term, but the explanation is entirely similar. So hopefully this illustration gives you a better feeling for why this works.